Good evening, good evening, good evening, everybody. I'm seeing in the chat already there's a couple of people there. Finn McEnroy, hello there, how are you? Tonight, as we can tell by the splash screen, it is moments. So let's take a moment to appreciate how important that is. That's the first bad joke of the evening. There's more where that came from. So what we're going to get on with tonight is we are going to get on with how things turn, why they turn, and how this is different to general forces. So if I take an object just randomly like this, let's take a little block and let's colour it in a bit. Let's make it a little red block. Okay, a little red block, and then we're going to try and give that a force. So we're going to put an arrow here and we're going to push this thing. Okay, and let's give it a certain number of newtons. Let's say we push it with 50 newtons. Now from our previous live streams on forces and on mass and acceleration, what we're really expecting this thing to do is to travel like this. Okay, it's going to go this way. And that's perfectly fine. In Newtonian mechanics, that's exactly what would happen, and is what happens. If this was hanging in space, this is precisely what would go on. It would just travel this way. It would accelerate, getting faster, faster, and faster. But what we want to do in this situation is we want to talk about, well, what happens if we make one part of it fixed? So I'm going to stick a pin in it here. Let's drill a hole or make sure that we have it held here somewhere. Now when I push this object, it definitely wants to go in a straight line, and this bit over here definitely does. The problem is that as it tries to pull all the other little atoms along with it, there comes a point where these ones go, no, I can't make it. I can't turn that corner. And as a result, the whole thing doesn't travel in a straight line. What happens is it follows an arc like this. It turns. All right, and how much it turns by and how quickly it turns is a matter of different physics, because Newton's laws apply to objects traveling in straight lines, either accelerating, decelerating, or traveling at constant speed. Now this is technically an object that's traveling around in an arc. As a result, it is accelerating because its velocity is changing, but that's not really what we're after here. What we're after is we're thinking, well, how much does it turn by? What does it need to turn? And what are the differences between things that do turn? Okay, so for example, let's imagine that we have, let's build ourselves a little room. Okay, and into that room there is a door. So let's view this from above. Okay, so there's a door, and we'll make it look door-like. There we go, one door. Okay, and the door has a set of hinges. So we'll set the hinge here. On this side, I'm going to make them grey so that we can see them. Okay, now this software is not the best at turning stuff, but what we want to do is we want to open that door. So we want to pop that door open and come in there. Right. Now, if it's a big heavy fire door, there's an issue. If a toddler walks up to that door and attempts to push it, it pushes it with a little feeble force and the door does not move. So an adult comes along, feeling sorry for the toddler, with a much larger force, pushes the door, and the door opens up, and the toddler looks up at you thinking that you're the most amazing thing in the world ever, how strong you are. Yep. So that means that there's some minimum amount of effort that's required to open that door. The funny thing about it is that if I take that exact same adult and make them push with the exact same force here, they will be unable to open the door. Finn, just checking in the chat here, I haven't seen the test, so I don't know if it's on your test or not. I'm imagining not, because it's a little bit further on, but it's worthwhile having a look at it anyway. Okay, so you won't be able to open this door. You won't be able to open this door from this position, and that means therefore that the force is not the only factor acting here. It certainly is a factor, because our little toddler couldn't open it, and that was simply because they weren't strong enough. The adult at the same spot was able to open the door. But the distance that you are away from the hinge also matters. And the further away you are from the hinge, the easier this is. And the bigger the force you can apply, the easier this is. So we can use that to essentially write the idea of the amount of turn that you produce. So the amount of turn is equal to the force multiplied by the distance from the hinge. Okay, now it's probably a multiply by. It's definitely not a divide. Because that would get it smaller. It's probably not an add because physics doesn't really work like that. So we can reasonably deduce that it's going to be a multiply by the distance from the hinge. And that would mean that in order to open the door, the amount of turn has a number. If I want to open the door, I need to produce 90 turn. Okay, whatever that happens to be. Now my force would be measured in newtons. My distance from the hinge would be measured in meters or centimeters or millimeters, I suppose. Force has to be in newtons. Distance, we can be a wee bit flexible on. Which means that my amount of turn would be either 90 newton meters, 90 newton centimeters. I'm pulling 90 out of the air here. It could be any number. Or 90 newton millimeters, depending on what we used our distance from. Okay, now we would love to call it the amount of turn. That would be sensible. Okay, we call it the amount of turn, give it a big capital T, and everybody would be happy with that. That would make sense. But in order to confuse people who are studying GCSE Physics, we don't call it the amount of turn, we call it a moment. Because that has absolutely nothing to do with what's going on, doesn't even remotely sound like it, and therefore we can mess you up in exams using it. Woo! I suppose the best way I can get you for remembering this is that if you're talking about sports, you talk about that was the moment that turned the game. Or when you're looking back at your life, that was the moment that turned my life around. Yeah, or that was the moment that my world got turned upside down by the most beautiful woman I'd ever seen. Okay, who's definitely my wife, but she's in earshot, so I'm hoping to gain some points there. Happy? Good, so moving on. So we call this moment. And this gives us our equation, that the moment equals the size of the force multiplied by the distance from the hinge. Now, we're not going to call it a hinge because not everything that turns has a hinge, but everything that turns does have a point that doesn't move. And that point that doesn't move we call a pivot. Now what I mean by a point that doesn't move is that if I take this object here, right, and I spin it, okay, so just spin it around its middle here, that every single point on it goes somewhere. So what I'm going to do is put a series of dots on this. All right, I hope that works. I'm going to group this together. And as I spin it, you should be able to see that all the dots go somewhere. Okay, with roughly the exception of this one here. Bear in mind I'm drawing this live. That one doesn't really go anywhere. It's not ideal. Okay, let's see if we can get this sorted out exactly middle. Can I move this guy here? I'll put another point. Stick him here. There we go. Right. Now as we turn, there we go. Everything moves except for that one in the middle. Eagle-eyed viewers will see what I did there. Alright, that point there is your pivot point. That's your central point of your turning. Okay, so if I was talking about this moving, in order to make it move like this, I would have to drill a hole where that little dot is there, okay, and make that thing turn around it. In easier examples, let's have a nice thin object like this, a simple seesaw. Okay, that when we place an object on the end of our seesaw, so let's place a child over here, okay, who's obviously been involved in some form of horrendous accident. There we go, child. Art is coming on well on the channel. Then this child's weight will push this down. This whole thing will turn this way. This side will go down, this side will go up, but this point here goes nowhere. It turns, but it doesn't move, and that's what a pivot is. Okay, so that's what we mean by distance from the pivot. Now, shortened form, that is moment equals F times D. I like to put a little FP in subscript there. You certainly don't have to, it's not on the mark schemes, but I like to remind myself when I'm working these things out that it's distance from pivot, because those sneaky examiners, what they will do is that they will, yes, thank you, Liam. His name is Herman. Yeah, Herman's a good name. What sneaky examiners will do is they will give you every distance under the sun except for the distance from the pivot, and you'll have to work it out. And we'll come to an example like that probably in the next 4 or 5 minutes. All right, so let's see what we got going on here. Now, the other problem with this is that let's imagine we have another child. Okay, so let's flip that horizontal left to right. Tell you what, see this, you're getting art and you're getting all sorts of things going on here. Let's imagine that this child is identical to Herman. Okay, this is Rudolph over here. Why not? German children on a seesaw. And let's imagine that they're kind of equal distance from the pivot point. Well, Herman over here, we'll need to label them. Herman and Rudolph. Okay, Herman is going to try and pull this thing down this way, which will cause the whole thing to rotate. And grab my pen. He's trying to rotate it like this. Okay, so direction-wise, he's trying to rotate the whole thing clockwise. Okay, because that's the way the clock goes. If you were to set a clock on the page here, then that's what it would look like. I'll keep it in red. Rudolph, on the other hand, is attempting to do the exact opposite. Even though he's got the same force and he's the same distance away from my pivot, he's trying to do the exact same thing but in the opposite direction. He's trying to push it anti-clockwise. And because they're the same distance from the pivot and because they're applying the same force, what's going on clockwise is exactly the same as what's going on anti-clockwise, and they cancel. And this leads us to a very, very, very important equation that's not actually in the notes, it's not in the course, but it's important for you to understand that the overall moment is equal to the moment in one direction, or the moment one way, take away the moment the other way. And critically, if the overall moment equals 0, then we can say that the object is not turning. That's kind of obvious. I hope that's obvious anyway, because your moment one way will totally cancel the moment the other way. However, hello logic error, just seeing you there. The other way around is also true, and this is the great thing about physics, that logic sometimes works backwards, and this is sensible. That if the object is not turning, then we can say that the overall moment equals 0. Now when you're seeing that on the screen, it seems like I'm being really, really redundant on this. Obviously that's true. But look around the room that you're in now, or wherever you happen to be watching this. If there is any object that is not rotating as you look at it, and I would imagine that's most of them, okay, if all the objects are rotating, you've taken something, seek medical attention. But if the objects are not turning, then their moments are balanced. Everything clockwise is equal to everything anti-clockwise when you total them up. Okay, so let's take an example and see how we get on, because that's what I said we were going to do. It's in our list at the side. We've got our equation, we've got our description, so let's get to it. Okay, so let's get ourselves a little pivot. You know what, we'll not use that. We'll use a top down drilled into the wall pivot. Okay, so let's imagine that we have a shelf hanging on a wall. We're looking at our shelf. We'll give that a little fill. So we'll give it a gradient fill. Everybody loves a good gradient. There we go. Look at that. Oh, we've used the same color. That doesn't really work. That's horrible. That's more horrible. Yeah, it's pretty horrible, but it'll do. There we go. Right, so there we go. We've got ourselves a shelf. And let's put a little hole here that we're going to drill into, and we'll put a bolt into that, so fill that in grey. Alright, now what we're going to do is we're going to apply a force to this. So pull this thing upwards like that. Alright, and let's put in a force of 20 newtons going upwards. Okay, 20 newtons going upwards, and let's give you a little distance here. Going across here. of 40 centimeters. So that's what we're after. 20 newtons, 40 centimeters. So what we're being asked to do here is to calculate the moment. So once again, we should have our FWAU formula working answer unit. Remember, all of our physics should look sexy at the end. You should be saying FWA. So our formula that we want is, this is a moments question, so it's moments equals force times distance from pivot. My working out now, I put the numbers in. My moment is equal to my force, which is 20, times the distance from the pivot, which is 40. No fanciness going on here, we're all good. Which leaves me, my moment is equal to 800. Okay, so that's my number, but I need my unit. I'll just compress that back up. Now, my force is in newtons, my distance is in centimeters, so my unit is Newton centimeters. And you would think that that's right, but remember that moments can be one of two ways. They can either be clockwise or anti-clockwise. That makes them vectors, and as a result, we need to have a direction in here. So what we do is we imagine that we set your pen down on top of your exam paper if you're doing this, hold it here where the pen is, and push it in the direction of the force, and your pen should move that way, round like that, and that is the direction that the clock does not go, so therefore that is anti-clockwise. So the overall turning moment created in this situation is 800 Newton centimeters anti-clockwise. That's pretty much one. Okay? Sorry, Finn. Didn't mean to get you in trouble there. Good. Now, moving on. So we've got that sorted out. Now what we want to do is want to make the situation a little bit more complicated. So let's ditch that for a moment, and let's go and get something a little bit more interesting. Okay, so let's get that out of there, and let's move our force out. Let's move our force out to here. Right. Change our force up a bit. Let's change it to 60 newtons. But this time we're going to play about. We're going to add another force in here. Get my arrow tool as opposed to my line tool. So we stick another force. We're going to have it going this way. We're going to call it 40 newtons. And then we're going to put some distances in. So what I'm going to do is I'm going to put, let's see what I can mess about with. Let's put this distance in. I'm going to give you this distance to the end of the thing. And I'm also going to give you this distance. Okay, so notice that I'm not giving you all the information here because I'm a sneaky examiner and I'm approaching my sneaky quota. So let's give that 15 meters. 15 meters is pretty big, but we'll go with that. So that's going to be, if that's 15, that's going to be about 7 meters. And then this whole thing is going to be 15, 7, 22, double that, let's say 40. No, we don't want to say 40 because we don't want too many 40s. 38 meters long. Okay, keep it vaguely to scale. It's not even close, but it'll have to do. It'll have to do. Now, what I want you to do is I want you to find the overall moment here. Okay, so the big problem here is that we've got a couple of forces, so we can't use one equation straight up. So we're going to use the moments equation twice. We're going to get our moments clockwise, get our moments anti-clockwise, and then we're going to use our previous equation here. We're going to get the overall moment is the moment one way, take away the moment the other way. Okay, so we're going with that idea. So once again, I set down my pen like this, and I go, right, this force is trying to push this thing this way. So this is the anti-clockwise one up for here, and I can write that as ACW. Okay, that's absolutely fine in exams, no problem at all. And this one here is pushing clockwise. And in the exam, write these things on it. It's your exam paper, write on it. You know, get yourself sorted out. Okay, so let's do the clockwise one first. So again, I would write down clockwise over here to sort myself out, let the examiner know what I'm trying to do. So clockwise, I've got moment equals force times distance from pivot. That my moment is equal to my force over here, and my force is 40, times my distance from the pivot, which is 15. Okay, so therefore my moment is equal to 40 times 15 is 600 Newton meters. And that is clockwise. Though it's in the clockwise column, it's a good idea to just put that at that. Over here then, we try the exact same thing with anti-clockwise, so anti-clockwise. And again, it's worthwhile writing out the formula. I've been doing this for years, longer than probably most of you have been alive. Still write the formula, keep my brain in that way of going. We are a pattern machine, so therefore, like, get into the pattern. Get used to doing the same thing over and over and over again. Okay, it's just habit. Okay, so my force is 60 times my distance from the pivot. Minor problem. I don't have my distance from the pivot because there's a bit missing. I've got all the other stuff going on here, so let's work that out. Okay, what I need, I'll give you a different color here. What I need is this distance here. Okay, so how do I get that? A little bit of maths here. What we have is 15 plus 7, that's 22. Plus my unknown distance, x, is going to equal 38. Because the whole distance here is 38 meters. Okay, so take 22 away from both sides. That gives me that x is 14 meters. Try again. Take away 22 from both sides. That gives me that x is 16 meters. I knew that I'd scaled this better. Okay, so 16 meters goes in here. But my distance from the pivot is not even that. My distance from the pivot, which we will put in beautiful purple, is this distance. The distance from the pivot point over to the line of the force. Okay, that distance there. And that distance, therefore, is a full 31 meters. Okay, we could have probably done that without that. We could have just taken the 7 away from 38, but it's worthwhile having a play. So 60 multiplied by 31 is our calculation that we want to do. Alright, so we go and grab our calculator, which I should have had handy. Let's get that on the screen. Calculator on. 60 multiplied by 31 gives me 1860. So 1860, again Newton meters, and that's in the anti-clockwise direction. So now I want my overall moment. Okay, so my overall moment, in this case, will be my moment anti-clockwise minus my moment clockwise. I know that because my anti-clockwise moment is the bigger one, so it's going to be anti-clockwise. I know that. So my overall moment is equal to 1860, take away 600. So my overall moment is equal to 1260 Newton meters. And that is anti-clockwise. And that's my final answer. Okay, now just before we go then, we've got 7 minutes left. We don't have time to get into the more complicated stuff. That'll be in a couple of weeks' time. But let's try something a little bit more interesting, a little bit more tricky, especially for those of you who are quite clever, because this is a pretty standard trick that's done that messes you up. It's supposed to help you. It's actually supposed to help you, but if you get yourself kind of sorted out, and get yourself weirdly in your own head, this can mess you up pretty badly. So again, we'll get ourselves a little block, grab our gradient fill, we'll make it, there we go, that's a beautiful kind of turquoisey colour that time. Turquoise? Yeah, is that a thing? Yeah, we'll go with that. Alright, so out in this one, we are going to put 500 newtons. We'll not even mess you about in the distances. Okay, we're going to be really nice about this one. Give you a nice distance from the pivot, even give you 10 centimeters away. And what I'm going to do here is I'm going to place a force X. Alright, so we know we're in business now because we've got some algebra popping in. And we'll give you a distance from the pivot here. Here we will give you this. We'll give you a distance from the pivot here of 7 centimeters. Okay, but I will tell you one thing. I will tell you that this system is balanced. Okay, that's it. And what I want you to do is I want you to, first of all, I'm going to try and talk you through it. I'm going to get my font right. I want you to find the moment caused by the 500 Newton force. Okay, I'm going to give you 3 marks for that because I'm a nice examiner. B, I'm going to ask you what is the moment created by the force X. I'm going to give you 1 mark for that because I'm getting stingy. And then C, finally, what is the force X? And I'm going to give you, again, I'll maybe give you 3. I might give you 2 for that, but we'll be generous now. So there's 7 marks altogether for this. So this is your moments question, and hopefully you get this. Hopefully you get this one. Okay, so the moment created by the 500 Newton force. Let's do our due diligence here. Get my pen out, set it in the pivot, put my finger on the end of it here, and push it this way. Okay, so this one here, this time, is my clockwise force. And we can reasonably assume that the other one's got to be anti-clockwise if it's balanced, and it is, so that's okay. So this is anti-clockwise. Okay, now all we're interested in is find the moment caused by the 500 Newton force. Not bothered about X just yet. All it's asking for is that one. So moment equals force times distance from pivot. Moment equals my force again, 500, times the distance from the pivot, which is 10. So my moment equals 5,000 Newton centimeters clockwise. 3 marks in the bag, 1 for that, 1 for that, 1 for that. Right, would have probably given you the Newton centimeters. Okay, so you wouldn't get the mark for the unit. Now here's the cool bit. We know that part B does not require a calculation, or any calculation that it requires is super simple. I know that because it's worth 1 mark. Anything that was vaguely worth giving you complicated stuff to do would be worth 2 or 3 marks. Calculations tend to be worth either 2 or 3. So this is a think about it. So what's going on here? This word here is what's going on here. Balanced, not turning, sitting still. Flick our way back. If the object is not turning, then the overall moment is 0. The only way the overall moment is 0 is if the moment one way is exactly equal to the moment the other way, just like Rudolph and Hermann back here. So, in order for this to be balanced for part B, it must be that the force X is creating the exact same moment, which is 5,000 Newton centimeters, but in the opposite direction, anti-clockwise. Okay, and that's you. You've got your 4th mark on the board, 3 to go. Now with that information, we will want to know what force X is. Right, so we're in business now. So we want to know what's the force X. This is a moments question, so it's moments equals force times the distance from the pivot. This time though, now we know the moment that's being created here is 5,000. We've worked that out. And that is equal to the force, which is X, times the distance from the pivot, which is 7. Okay, we don't want X times 7, we just want X, so we divide by 7 on both sides. Divide by 7, divide by 7. Gives me, calculator back out, 5,000 divided by 7, 714.29. 714.29 equals X. Big X. So X is equal to, now wait for it because there's the last little sting in the tail, 714.29 just newtons. Remember, the whole way through this is a force. Watch for the unit. Really common mistake here is for people to get all excited and start writing Newton centimeters. 714 newtons here. And this is actually something called the principle of moments. And you can do this a little bit faster. We'll maybe talk about that the next time we come along. Is that you can start with the concept that if a system is balanced, then the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So as my parting shot then, this is called the principle of moments. And it comes in 2 parts. That if a system is balanced or in equilibrium, if you like your fancy words, if a system is balanced or in equilibrium, the sum or the total clockwise moment equals the total anti-clockwise moment. And this is one of those starter questions that leads you in, okay, that when you get to question 4A part 1 might just be state the principle of moments. And it'll be 2 marks. Generally 2 marks, and the 2 marks come for the 2 parts here. Most people get the second part. Total clockwise moment equals total anti-clockwise moment. Loads of people forget this top bit here. If a system is balanced or in equilibrium. Because it's not true if it's turning. Alright, so that's us. That's us for tonight. There's a worksheet below that gives you a similar question to this. I strongly recommend you have a little crack at that. It'll only take you 3 or 4 seconds to get through it, but you'll definitely understand the stuff at the end of this. Thank you so much for turning up, and all that remains to be said is, of course, physics rocks. It's true.